Hello, and thanks for clicking on this next Prenarculus production. Today, we're going to have a review of functions as well as function notation. And then at the end of function notation, we're going to make it a little more tougher than you're used to, probably for evaluating functions and make things a little bit more interesting. So let's get started on reviewing some things involving functions, function notation, and then we'll go from there. So what is a function? A function is just a relation, okay, that maps each element x. Remember, your x values are your domain, and to exactly one element y, exactly one element of the range. So the easiest way for me to hopefully remind you about what is and is not a function is to imagine this simple machine that you put your name into, and then the machine will tell you how tall you are. So basically, you put your name, a piece of paper with your name into the machine, and then the machine just spits out a piece of paper and says, "This is how tall you are." So let's see how this machine would work. So let's say I had an input, which are my x values, and my output are my y values. Let's say I input my name. If I input my name, the machine should output 5'9" because that's how tall I am. So let's pick somebody. Let's say Bob. We input Bob's name, and Bob is 6'1". Okay, wonderful. And then let's say we have Ruth, and we input Ruth's name, and Ruth is 5'7". Okay, so this machine is obviously working properly, provided these are our actual heights. My height is 5'9", Bob's is 6'1", and Ruth's is 5'7". This is an example of a function. Okay, this input-output table or XY table represents a function. All right, each element X has exactly one element Y. My height is 5'9", Bob's height is 6'1", Ruth's height is 5'7". Okay, so now let's take the same machine and let's see what happens to it now. Take that same machine, put my name in, and 5'9" comes out again. Put Bob's name in. Bob is 6'1". Let's put my name back into the machine again. If I put my name back into the machine again, then we know what the output should be. It should be 5'9". That's how tall I am. It doesn't matter how many times you put my name into the machine. My height shouldn't change. But what if it said now that my height is 5'4"? Well, you would probably say, well, there's definitely something wrong here because NAR can't be 5'9" and 5'4" at the same time. So this is not a function. The machine doesn't work properly. It's not a function. Okay? I can't have two different heights. Okay? My input, my x value, my name doesn't have exactly one output. It has two different outputs, 5'9" and 5'4". That's an example of something that's not a function. Now let's go to the one that sometimes gets folks, and let's make sure that you understand the difference. Let's say I put my name in, 5'9" comes out. Bob puts his name in, 6'1" comes out. Ruth puts their name in, 5'7" comes out. And let's say we have Harry. Harry puts their name in, and 5'7" comes out. So the question is, you have to ask yourself, does the machine work properly? Right? Does it work properly given this input and output from the machine? Is it possible that both Ruth and Harry can be the same height? Well, I think the answer to that is obviously yes. There's a lot of people in this world that have the same height. So that's certainly possible. There's nothing wrong with that. Ruth has a height. Harry has their own distinct height. This is a function. Okay? That is also a function. Now, if I were to take Harry's name and put it in again, and now Harry's height is 5'2". Now, this is not a function anymore because Harry has two different heights. Harry can't have two different heights, okay? So it's not a function. All right, let's take this one back to where it is a function again. Okay, that's a function. All right, so now the moral of the story is this. It's okay for y values to be repeated, right? It's more than okay. It's possible that two people can have the same height. Three people can have the same height. Four different people can have the same height. The issue with functions is the x values cannot be repeated. If the x value repeats and it spits out two different y values, then it's not a function anymore. Okay? That's the difference between what is and what isn't a function. Now, there are three ways to represent a function. The first one is numerically, using a table or list of ordered pairs. So let's say we had a table, 3, 5, 7, 2, 1, 6. This is certainly a function. Each x value has its own y value. Each person has their own height. Okay, this is a function. Let's say I had a table that looks like this. -5, 7, 9, 8, 1, 1. Okay, that's also a function. This is definitely a function, right? Each person has their own height. Person 5 is 8 feet or whatever. Person 7 is 1 foot. Person 9 is 1 foot. Now, two people have the same height. That's okay. That is a function. Okay? What's not a function? Well, person 1, 2, 3, then person 1 again, 4, 7, 9, not 4. Oops, that's the highlighter. I do that all the time. 2. Person 1 is 4 foot tall. Now they're 2 foot tall? No, that's not a function. Okay? Because the x value repeats, one x value has two different y values. Okay? One x value has two different y values. All right? You can also list them as ordered pairs. For those of you who have issues with figuring out if the set of ordered pairs is a function, what you can always do is write it as a table. A lot of folks like to see it as a table instead. And yeah, that one's a function. Okay, so if you struggle with the writing it horizontally, just write it vertically, and you'll be able to see it pretty fast, hopefully. All right, so numerically, that's one way to do it. The next way to do it is graphically. We decide if functions are, or if graphs are functions using the vertical line test. If a graph represents a function, then every vertical line drawn through the graph will only intersect the graph at one point. So if I draw this parabola, no matter where I draw a vertical line through this parabola, it will only intersect the parabola one time. This is a function. The parabola is a function. If I gave you a circle and said, is it a function? You would say, well, here's a vertical line. It touches the graph more than once. It touches it twice. So this is not a function. It fails the vertical line test. Okay? If I were to draw for you whatever this is, a Z or an S or something, remember, all you need is one vertical line to touch the graph more than once, and it's not a function. So if I were to draw a vertical line here, 1, 2, 3 times, that's not a function. Okay. I don't care that if I drew a vertical line over here, it only touched once. Doesn't matter, because I found a vertical line that touched more than once. So I know for certain it's not a function. That's your vertical line test. You've done that many times before. Algebraically, using an equation, function notation, f of x represents the variable y. If I were to ask you to graph the line y equals 2x minus 5, it's the same thing as me asking you to graph f of x equals 2x minus 5. Y and f of x are the same as each other. Yes? F of x is a fancy way to say y. F of x allows us to say, okay, this graph, y equals 2x minus 5, I already know it's a function because I'm using function notation with it. Since I'm using this notation, I know that whatever I graph must be a function. It must pass the vertical line test. I know that for certain already without doing any work or making the graph. Okay? That's one of the things we use it for. All right, let's go and evaluate using function notation. So this you've done before. If f of x is equal to 4x plus 7, and I ask you to find f of x, then everywhere you see an x in f, you're going to replace it with a 6. Here's an x. It's going to be replaced with a 6. And I'm going to do the math. 6 times 4 is 24. Add 7 more. So f of 6 is 31. What does that mean? That means that 6 comma 31, the x value is 6, the y value is 31, because remember, f of x is just y, is a point on the graph f of x equals 4x plus 7. So if I were to graph the line y equals 4x plus 7, slope is 4 over 1, y-intercept is 7, then it would pass through the point 631. Okay, 631 is a point on this graph. I know that for certain. All right, see if you can try letter B here. For letter B, g of x equals negative 3x squared plus 7x minus 2, and I want you to find g of 2. To find g of 2, we're going to replace all the x's with 2's. So we have negative 3, 2 squared, plus 7 times 2 minus 2. G of 2 is going to be negative 3 times 4 plus 14 minus 2. G of 2 is negative 12 plus 14 minus 2. G of 2 is 2 minus 2. G of 2 is 0. So I know 2 comma 0 is a point on g of x equals negative 3x squared plus 7x minus 2. If I were to graph this parabola, 2 comma 0 would be a point on it. I know that for certain. That's how we evaluate functions using function notation. Okay, now let's make the function notation or some of the evaluations a little bit more complicated. Let's say I asked you to evaluate h of x equals radical 3x plus 1 plus 5 and find h of 2a. So before we do that, let's come down here and let's say I asked you to find h of, let's just say h of 2, not h of 2a. We'll do h of 2. So I know that I'm going to replace all the x's with 2's. So let's do that. Square root 3 times 2 plus 1, close that off, plus 5. So h of 2 is going to be the square root of 6 plus 1 plus 5. H of 2 is going to be the square root of 7 plus 5. I can't add these. They're not like, right? I can only add radicals that are like. So this would be my answer. H of 2 is radical 7 plus 5. That's the correct answer. Okay? Now, instead, I want you to evaluate for me h of 2a. To evaluate h of 2a, you're going to replace all the x's with 2a's. So instead of writing x, you're going to write 2a in its place. Here's an x. I'm going to write 2a plus 1 plus 5. So h of 2a is going to be square root of 6a plus 1 plus 5. And that's it. I can't do any more with this. So this is my answer. Okay? Let's try letter D. So letter D asks us to take j of x equals x squared minus 3x plus 4 and find j of x plus h. So before we do this, let's actually go ahead. We'll do it down here. Let's move this up. We'll do it down here. Let's find j of 4x. Okay, so in place of x, I'm now going to write 4x. Everywhere I see an x, there's going a 4x in its place. So here's an x. In place of x, I'm putting 4x in parentheses and squaring it. Minus 3. In place of x, I put 4x in parentheses, plus 4. So now, 4x squared, 16x squared. Negative 3 times 4x, negative 12x, plus 4. I can't combine any of those. None of these are like. So this is my answer. 16x squared minus 12x plus 4. I'm done. Okay? I can't do any more. All right. Now let's come up here, because this one up here is even a little more complicated still. I want to find j of x plus h. It's the same idea. Wherever I see an x in j, I'm going to put an x plus h in its place in parentheses. Here's an x. So in place of that x, I am putting x plus h and squaring it. Minus 3. In place of x, I am putting x plus h plus 4. And now I'm going to do the math. So I have to do x plus h squared. Well, that means write it twice and multiply it. So I have to double distribute or FOIL. X times x is x squared. X times h is xh. H times x is hx. H times h is h squared. These two are like terms. They're not in the correct order, but they're still like. So that's x squared plus 2xh's plus h squared. So now I have x squared plus 2xh plus h squared. This, x plus h squared, is this, x squared plus 2xh plus h squared. Now I'm going to take this negative 3 and I'm going to distribute it. That's negative 3x, negative 3h, plus 4. I can't combine any of these. None of them are like. The x squared is not like to x. The h squared is not like to h. There's no 2x, there's no xh's in this. So this is my answer. This idea of being able to take a function and evaluate it at x plus h is extremely important. We're going to do this coming up soon. We're going to evaluate the difference quotient, it's called. And you have to be able to take a function and evaluate it at x plus h. So this example is really, really important. Okay? And that's it. That's how you evaluate a function. That's how you identify a function. And as always, thanks for clicking.